27 years ago, at the University of Geneva, Michel and Didier Queloz, now a professor at ETH, discovered the first exoplanet orbiting a star similar to the Sun. Much has happened since that initial discovery. Astronomers have identified more than 5,000 exoplanets. Many of similar size to Earth, in more than 3,700 different planetary systems. With only a small portion of the universe analyzed so far, it certainly seems plausible to suggest that life may exist on other planets beyond our solar system. However, as any scientist will tell you, a plausible hypothesis is not the same as proof. This has led many researchers to wonder how we could demonstrate the existence of life beyond our solar system. A promising approach is to analyze the atmospheres of exoplanets. By studying the absorption lines in the optical spectrum of a host star, scientists can determine which molecules are present in the atmosphere of an exoplanet, at least in the case of larger planets. In addition to hunting for signs of methane, carbon dioxide, oxygen, or water vapor, they are also interested in identifying the combinations in which these substances occur. Both methane and oxygen are present in the atmosphere of Earth, says Sascha Quanz, professor of exoplanets and habitability at ETH Zurich. This is a chemical imbalance that would not exist without living organisms. In other words, life must have caused this imbalance. The discovery of such an imbalance in the atmosphere of an Earth-like exoplanet would be a strong indicator of the presence of life. Ideally, of course, it would be better if we could capture direct images of exoplanets instead of observing them indirectly as they pass in front of their host star. However, this is easier said than done, because exoplanets are almost completely obscured by the brightness of their parent stars. To solve this problem, Quanz has joined with other researchers to develop an instrument for the Extremely Large Telescope, ELT. Construction of the ELT in the Atacama Desert in Chile is underway and, once operational, the 39-meter mirror of the telescope will greatly increase astronomers' ability to observe deeper into space. With the ELT, we will be able for the first time to capture direct images of an Earth-like planet orbiting a nearby star, because this new instrument will block the light from that star, says Quanz. But where should researchers focus the search for life? And what signs should they be looking for? Some clues may be found in physical models, such as those developed by Judith Szilagyi, assistant professor of computational astrophysics, and her group. These models can be used to reconstruct how planets form over time from the initial protoplanetary disk of dust and gas that orbits around a newly formed star, and also help determine which objects warrant further detailed inspection via telescope. Szilagyi builds models that take into account a wide range of factors, including gravitational forces, magnetism, gas movement, and how starlight interacts with the disk material. By calculating countless different combinations of these parameters, we can get an idea of the diversity of planetary worlds that may exist in the universe. However, experience repeatedly shows that nature often has more up its sleeve than models predict. For example, the first exoplanets caught the scientific community by surprise because astronomers had never suspected that giant planets the size of Jupiter could orbit so close to their host star. Researchers were equally intrigued by the existence of so-called super-Earths, which are rocky like Earth but about 1.5 times larger. Szilagyi recognizes that her models regularly prove to be inaccurate and require recalculations, but she remains optimistic. This constantly leads us to rethink our ideas about how planets form. One of the key questions Szilagyi hopes to answer with her models relates to the origin of water. Life on Earth requires water, she says. Hence our interest in places that show signs of water. These bodies may even be found within our own solar system, and astronomers are eager to learn more about them in the coming years. They include Jupiter's moon Europa, which likely harbors an ocean beneath its thick icy crust, and Saturn's moon Enceladus, where scientists have observed sources of ice particles emerging from the surface. Geology can also provide useful clues to the composition of alien worlds in other planetary systems. Paolo Sassi, assistant professor of experimental planetology, investigates the exotic minerals, liquids, and gases that make up the interior and atmosphere of other planets. We simulate a wide range of conditions in our experiments, he says. They help us build a picture of what's happening on a planet's surface and what's happening inside it. Our knowledge of the chemical composition of other planets is still incomplete, which makes Sassi's task more challenging. Examining the optical spectrum of the host star gives us an initial idea of a planet's chemical composition, says Sassi. It provides the basis for understanding which elements are present and in what quantity. By combining information about the mass and diameter of various planets with modeling results, scientists can deduce how different elements are actually distributed throughout the planetary system around the star. Our own solar system is a useful reference, because 60 to 70% of all stellar systems studied so far have a similar chemical composition. Sassi is therefore using numerical models to try to gain a better understanding of how the Earth and its neighboring planets formed. This gives him the information he needs to reconstruct the masses, number, and distribution of planets around other stars. However, there are also stars that have a chemical composition that is entirely different from that of our Sun. For example, a star may contain more carbon and less oxygen, which may mean that the planets that orbit it are composed of minerals different from our Earth. The predominant minerals on such carbon-rich planets may be silicon carbide and titanium carbide, or even diamonds, says Sassi. This, in turn, would have an impact on the planet's atmosphere. For example, rain on such a planet may consist of droplets of graphite instead of water. Ultimately, the success of our search for alien life depends on a combination of different factors. Telescopic observations, laboratory experiments, and numerical models are undoubtedly key elements in any research program. But we will also need intelligent algorithms that can collect as much scientific information as possible from vast amounts of data, as well as instruments that provide the precise data that researchers need. The development of instruments is a priority for planet researchers like me, says Quanz. As researchers, we need to understand how the instruments work to know what kind of information we can get from them. A long-term perspective is also essential, so Quanz is already thinking one step ahead. He is responsible for an international initiative that aims to make major strides in the search for alien life. This is part of one of the large-scale scientific missions that the European Space Agency (ESA) is launching between 2035 and 2050. We are reaching the limits of what we can achieve with ground-based telescopes, because all the molecules we are looking for also appear in the Earth's atmosphere, and the Earth's temperature is similar to that of the exoplanets that interest us, he says. If we want to escape the tremendous background noise created by Earth, we have to go into space. It may be the only way to detect traces of life in the atmospheres of exoplanets. Unfortunately, however, there is no way to install space telescopes as large as those in the Atacama Desert. Quanz and his colleagues have therefore proposed a bold project, known as the Large Interferometer for Exoplanets, LIFE. The idea is to position 4 additional small telescopes at the second Lagrange point, where the James Webb Space Telescope obtained the spectacular images that recently impressed the world. By combining measurement signals from several small telescopes, we can achieve a resolution similar to that of a single larger telescope, says Quanz. This will allow us, for the first time, to obtain direct images and chemically characterize dozens of Earth-like planets. Before this happens, scientists will need to solve a whole series of technical challenges. The telescopes need to fly in a very precise formation that changes every time a new planetary system is targeted. The measurement signals from the individual satellites must be synchronized with tremendous precision, and the telescopes must be equipped with extremely sensitive sensors, designed to capture the little light that emanates from the planet. Equally critical is the question of how the satellites will be powered, as repositioning them requires substantial amounts of fuel. All of this is technically feasible, Quanz says, but it will require a great effort not only from scientists, but also at the level of research policy. Ultimately, it is a matter of priorities, he says. For the first time, we have the chance to offer an empirical answer to the question of the existence of extraterrestrial life. Finding that answer would fundamentally transform our view of the world. It is not an opportunity we should lose.